Okay, so welcome back. We are continuing with on-chip antennas. Next topic is loop antennas. Loop antennas has very interesting characteristics. If we consider one lambda loop, which is a resonating loop, in that case maximum radiation it comes in the broadside direction. But for a small loop, radiation is in the plane of loop, maximum radiation. When we are going to use loop antenna on chip, obviously it will be a resonating loop antenna and we are expecting radiation in the broadside direction. So, let us see this example. We are having one wire loop antenna and its length is 1 lambda at the operating frequency, and typical gain we get from 1 lambda loop is more than 3 dBi. But when we fabricate it on silicon, because of those increased losses, realized gain always less than 0 dB, will be having some negative value. In this particular example, this loop is being fabricated on BCB material, which is placed on that silicon. It will to some extent it will improve the gain or antenna efficiency. We may have also complementary structure. So, here in left example, it is a wire loop, it is being fed by coplanar strip line, CPS line, and its dual structure right hand side, it is a slot loop having almost similar characteristics. So, look at the feed lines. Here we can use simply CPW feed lines. In the right hand side figure, we have one advantage. The advantage is that the outside ground plane, it is really narrow and it can be used as a second radiator. So, that means as if we are having two coupled resonating structure and which increases the bandwidth of this antenna. This type of technique is very common for bandwidth improvement of any antenna. And now, we have a thumb rule again here to avoid surface wave mode generation. F should be, operating frequency should be smaller than this cutoff frequency Fc, which is given here, square root of 2 by epsilon r minus 1, and it is a function of h, thickness of the substrate, and also A is given as epsilon r if we have TM type surface wave mode, otherwise A is equal to 1 if we have TE type surface wave mode, and n is an integer. And not only that, for a ground backed CPW, n is odd for TE and n is even for TM mode. This is one fabrication example from IBM. It is designed for 35 gigahertz applications and typical dimension it is shown left to right is 3.2 millimeter, and you can identify the antenna structure. We have a slot loop fed by the CPW line, and also we have a ground plane, and look at the S11 plot. Its bandwidth is quite high. The matching bandwidth here, you see we can't even achieve minus 10 dB of input impedance, but for handheld device application sometimes 3 dB bandwidth is enough. Here they are considering 3 dB bandwidth, matching bandwidth, and it is quite wide due to the ground plane resonance. Antenna radiation pattern. So, again in the E plane radiation pattern, in this side we do not have any significant radiation. This is not because of antenna, this is because of the measurement setup, because this side radiation is blocked by the probe station. It is being measured in using a probe station. We do not have such problem in H plane radiation pattern. So, now we know how to choose the type of radiator. So, next how to integrate them inside chip, because in chip also we have circuits. So, if we use any metallization for the circuit implementation, obviously there will be coupling. between that metallization used in circuit and the radiator. That is why radiator it should be placed as far as possible from the circuit part, and when we implement circuit, the metallization for inductors it is having the widest area. So, if there are inductors on chip inductors, in that case the inductors and antenna they should be placed on opposite side of the chip to avoid any coupling. Not only that, we can use some sort of guard ring around the antenna structure to avoid the coupling between the circuit and the antenna radiator. Typical this is one example. We are using two folded loop, one for the receiving side, another for the transmitting side, and you see one interesting thing, the antenna gain for the transmitting side is just minus 7.5 dBi, while for the receiving side it is minus 2 dBi. Why so? This is due to the coupling between the circuit part and the antenna radiator. Here they are not using any guard ring or any precaution, just they are placing the antenna radiator away from the circuit part. And now we put maximum importance on the receiving antenna, since the received power is very small and we have to detect it. And for this type of antenna, sometimes we do not care about the input impedance. It may not be 50 ohm system, it may not be 100 ohm system. What we do, the antenna input impedance it should be just complex conjugate of the next stage, that means the LNA. For this typical application, the receiving antenna input impedance is 70 plus J 40 ohm. This is to match the LNA input impedance, because LNA input impedance at the operating frequency it is not 50 ohm, something else. We need a complex conjugate of that to transfer maximum power to antenna or from antenna to LNA. So, some other issues when we go for circuit integration, radiator it should be placed on top metal layer. For gallium arsenide fabrication is use side space. So, circuit it grows side by side, and for silicon fabrication it use vertical space. So, it goes top layer by layer. Then antenna it is a radiating structure, it should be placed on the top layer always. The second point, already we discussed that antenna is placed in a different part of the chip to avoid any coupling. Then we have to use some separating layer between the radiator and the silicon substrate. Usually the silicon oxide layer is so thin that cannot be used as a substrate. Now, if there is any metal below this radiator, there will be obvious coupling between the radiator structure and the metal. So, we can't place any metallic structure below radiator. We have to keep in mind this point when we are going for on chip antenna design. Ground shield, if it is available, if it can be used as the reflector if the fab process it supports, and if there is any passive component, for example inductor which you discussed, it should be far away from the radiator. We have to also avoid LO leakage. In silicon substrate we have the surface wave mode and we have leakage from local oscillator and it can damage the receiving side of the antenna. Next, packaging issues. In practice, always we will be using some sort of packaging material to protect the chip from different weather condition. It is showing a scenario like that. A globe top encapsulation is being used as the packaging material. Then whatever material we use for packaging, it is usually lossy material. It will further deteriorate the antenna efficiency. or your antenna gain will decrease. So, not only that, the packaging material whenever we are going to use, it should be transparent to radiation. Otherwise, electromagnetic wave whatever being radiated by the radiator, it will not come out. We have to keep in mind also when we are selecting any material for the packaging. This packaging layer itself, it can support surface wave mode, and again we may have coupling between the antenna structure and external circuit. That point also we have to keep in mind. So, typically people use metal rings or cavities to isolate the radiating structure from rest of the structures. Now, next is interconnect issues. Once we have the radiator, we have to connect it to microstrip circuit. So, how to connect? We can use obviously microstrip line, CPW line if possible, or we can use wire bonding. That is the most popular method to connect the radiating structure with the microstrip with the millimeter wave circuit part. Now, there are different types of connecting procedure. Popular one is the wire bonding and another one is the flip chip attachment. Flip chip attachment, it will provide you lower inductance and it is less lossy, but at the same time surface wave mode generation, it can be more for flip chip attachment. So, depending on application, depending on fab process, then we can select the type of bonding. It can be wire bonding or it can be flip chip attachment. So, here it is showing a typical flip chip attachment. In the right hand side, left hand we have CPW line. So, left to right it is being connected by wire bonding. Any metallic wire, if we use some bend, it is associated with inductance, and wire bonding, it is always forms a part of a loop. It is always associated with some inductance which we can't avoid. We have to properly model that wire bonding when we are going to use at millimeter wave frequencies. Otherwise, we will be facing input impedance matching problem. So, finally, how it looks when we go for integration. This is a scheme suggested by IBM. So, let us say we have the integrated circuit here on silicon, then antenna, it is being fabricated in laminates. So, this is not on chip antenna, but antenna as a part of packaging, and the antenna radiator is connected to MMIC by using flip chip attachment in this particular example, and right hand side you can see we have a support for the substrate, it can't hang in air, and below the radiator we have air cavity that will improve the efficiency of the antenna. This below structure you can see we have a folded dipole antenna fed by coplanar strip line, and we have one more guard ring here backed by metallization, metal ground. It forms like one cavity. We can call it a folded dipole backed by a cavity. This is the zoom in view of the structure of the this is a dipole antenna with similar structure, guard ring, and right hand side it shows the photograph of the fabricated structure, and look at the gain. Previously we are getting typical gain value below 0 dB. Now, with all these precautions, when we could avoid coupling between the radiator and the MMIC structure, not only that, power coupled to substrate we could also avoid in this, because we are using some air cavity for that. We can improve the gain to 6 to 7 dBi. So, these are some techniques, standard techniques used at millimeter wave frequencies to improve gain of the antenna, and the total size is 7 by 11 millimeter, including the antenna structure itself. So, that is all on chip antennas. The next topic we are going to start is leaky wave antenna. So, till now whatever we have discussed, we are using some sort of resonator structure and its length is typically lambda g by 2 or lambda g at the operating frequency. Now, we will see some of the antenna, another group of antennas where the antenna length is much more compared to lambda g, and these antennas sometimes they radiate throughout the structure, sometimes they radiate from the dielectric air interface or metal dielectric interface, and this group is known as travelling wave antennas. Now, under travelling wave antennas again we have two different categories. If you remember beta by k naught value, so if beta by k naught it is less than 1 for a guiding structure, that means it is supporting fast wave, and if beta by k naught is more than 1, it is supporting slow wave. Now, under travelling wave antennas we have fast wave antennas and slow wave antennas. Slow wave antenna example is Vivaldi antenna. These antennas radiates from discontinuities, and fast wave antenna it forms the group of leaky wave antenna. They radiates throughout the structure. At millimeter wave frequencies they are popular. Why? Because of its dimension. At low frequency, if I want to fabricate an antenna structure of typical dimension 10 times of lambda g, it will be huge structure, but at millimeter wave frequency you do not face any problem. And we have advantages such as the design is very simple, feeding structure is very simple, and it is less lossy also, since we are using increased volume. So, let us then concentrate on leaky wave antennas. What are the characteristics of leaky wave antennas, how they radiate, what are the different structures possible at millimeter wave frequencies. Some basic characteristics: since this structure it leaks power throughout its length, so we have to use the complex propagation wave number kz. We have both alpha part and beta part. It will be basically a wave guiding structure with some sort of semi open or open structure, so that it can radiate or leak power throughout its length. Then the alpha part is non-zero for the guiding structure. Beam direction is controlled by phase constant beta. We will see that beam direction it depends on the beta value, and beam width it depends on the attenuation constant alpha. Smaller the attenuation constant alpha, smaller is the beam width of the antenna. Then main beam cannot be in broadside direction for conventional leaky wave antennas. We will discuss now one by one. Now, under leaky wave antennas we have again two different categories. We may have uniform leaky wave antenna and we have periodic leaky wave antennas. Here are the examples shown here. You can see a rectangular waveguide where one longitudinal slot is placed on top of the on the top wall, and it is one example of uniform leaky wave antenna. It usually radiates along the length. So, we have leakage along the length, it comes out as radiation, and inside for fundamental mode operation we have TE10 guided wave mode. So, for this guided wave mode, then we have to consider both alpha due to the leakage loss and beta. Now, you see waveguide itself, it has some loss from the structure. So, whatever alpha we will be calculating here, it will be having the radiation loss and also the power lost inside the wave guiding structure itself. So, it has mainly two components. The second example is periodic leaky wave antenna, and for the periodic leaky wave antenna, the guided mode usually slow wave mode. Even for the slow wave mode, we can have power leakage and effective radiation, but it can be shown that radiation for a periodic structure, it is again coming only from the first wave mode. Then from where this first wave mode appears? If we analyze this structure, any periodic structure, it can be shown that any mode propagating along the structure, it is the summation of infinite Floquet modes, and at least one of these Floquet mode, it will be first wave, and we will be having radiation only from that mode, which is first wave. Let us continue with the uniform leaky wave antenna. This is a typical example. Here it is shown for rectangular waveguide. We are measuring the beam direction from broadside direction. It is given by theta m. As we discussed, the propagation constant, it is complex here. It can be written as beta minus j alpha. Then main beam direction, it is being determined by beta. So, sin theta m approximately that is equal to beta by k naught. Now, one interesting thing, already we know the beta by k naught variation. For a typical rectangular waveguide, it is shown here. It is for TE10 mode, it supports first wave, and always beta by k naught is less than 1. Now, with frequency, beta is changing, beta by k naught is changing. So, what we expect then? If I change the frequency, theta m will change. At cutoff frequency, beta is 0. In that case, beta by k naught is 0. In that case, we have a radiation in broadside direction. But since it is at cutoff, input impedance is infinite, we do not have any wave propagation inside, we do not have any radiation in the broadside direction. Radiation will start with some positive value of theta m, maybe 5 to 10 degree, and then as we increase beta, as we increase frequency, operating frequency, then beta by k naught increases. So, theta m will increase, and the highest possible value where beta by k naught converges to 1, and it is approximately 90 degree. So, for this type of antenna, scanning is possible by frequency sweep. If we change frequency, accordingly beta by k naught will change and theta m will change. So, by frequency sweep we can scan one quadrant, but what we see from this relationship, this scanning beam is always in one quadrant, and we can't achieve any radiation in the theta m equal to 0 degree direction and theta m equal to 90 degree direction. So, typical values we have 10 to 20 degree theta m to 70 to 80 degree. And now, if I use some dielectric inside the rectangular waveguide. So, if you remember, for dielectric loaded waveguide, this beta by k naught, it starts from 0, then it crosses beta by k naught equal to 1 point. That means, this whole radiation pattern, it is shifted to theta m equal to 90 degree, or we can go very near to end fire direction, theta m equal to 90 degree. So, this is the dependence of theta m on beta. Next, the antenna characteristics, how it depends on alpha, leakage rate. So, how we can control leakage rate for this rectangular waveguide? Just like the resonant antenna, as we have seen. If we place this slot near central axis, then we do not have any radiation from this slot, because we can't excite the slot in that case. So, we have to use some sort of offset. If I increase offset, in that case radiation will increase, or leakage from this slot will increase. Leakage also can be controlled by changing the width of the slot. If I increase the width, it will have higher leakage from the slot structure. And now the beam width of this radiation pattern, it depends on the leakage rate. Considering let us say 90% power is being radiated, then half power beam width delta theta, this is approximately 1 by L A by lambda naught into cos theta m, where L A it represents the total loss over this length. Radiation efficiency eta rad, this is given by 1 minus e to the power minus twice alpha L A, sorry, L A is the total length of this slot from left to right. So, for smaller alpha we have to use longer length L A to radiate at least 90% power and to have narrow beam width. Some other properties already we discussed some of them. Scan only in forward quadrant, this type of antenna, and it can have near end fire radiation pattern when beta by k naught approaches 1, and if we use some dielectric material inside, then this radiation pattern shifts to end fire direction. So, we will take a break, then we will continue with this antenna.